I've danced for almost all my life. I took my first class at 18 months, and the Washington Ballet has been my home since I was 5. Throughout my life, I was told that I had to choose between dance and a stable life, dance and my interest in STEM. But now, here's my attempt to reconcile the two. Maybe there is a way to combine both.
Ballerinas do releve in their pointe shoes. John's friend Katya does releve by standing on her toes in her shoe. We can model the arch of Katya's foot as she stands on pointe as a concave down function. The equation of the arch of her foot is y equals 7 minus 21 over x to the negative 2.
Here, Haley is doing an arabesque. One of her legs extends straight behind her to infinity, creating a graph modeled by the function 1 over x minus 3 plus 2. We can find the area under the curve first with improper integrals. When using improper integrals, you must write a limit statement. The limit for this problem goes to negative infinity, which we replace with a. Then we take the integral and evaluate it from a to 2. We get an infinity in our answer, therefore the graph diverges and the sum is infinite. We can also use the comparison test to find the area under the curve. We can compare this function to 1 over x. Since 1 over x is a harmonic series, it diverges. 1 over x is smaller or under the arabesque graph, therefore the graph of the arabesque also diverges.
Tendu is one of the most basic elements in ballet. Katya moves one of her feet outwards as the other one stays on the ground. When her foot moves out, she points it so the distance between her hip and the end of her foot increases as the angle between her two legs increases. We can make this into a related rates problem. In this problem, we will find the rate the distance between Katya's 2 feet is changing when the angle between her legs is 27 degrees.
Here, Isabelle is doing piqué turns, one of the many types of turns in ballet.
As you can see in this video, Kai is doing a turn. While she is doing fauteuil, in the middle of the fauteuil, she does do pirouettes. Pirouettes are turns when she holds the passe and turns on one leg. If we take Kai's straight leg as the axis of R, we can do a solid of revolution problem with the triangular shape of her leg.
Girl, you better not be speeding on the highway, cause the MVT will catch you, yo. I'll be watching you, yo. Don't mess with me, yo.
Lily's mom is late to pick her up as usual, so she must speed in order to get to practice on time. The time it takes for Lily's mom to drive from the mile 3 marker to the mile 9 marker on I-270 is 4.5 minutes. A nearby cop assesses her speed and finds that she is indeed speeding. Let's look at the math.
Lily is now throwing her ball forward and up, like an object in projectile motion. If we know parametric equations for the x and y positions of the ball, we can eliminate the parameter to find equations for the velocity and acceleration of the ball at a point in time. Ribbon is one of the pieces of equipment that we use in rhythmic gymnastics. As shown in the video, Lily is making spirals around the ribbon stick. Because the size of the spirals gets smaller the farther you move up the stick, we can describe the shape of the spiral using two functions. Then we can find the volume of the solid the ribbon makes by summing up infinite circular cross-sections perpendicular to the x-axis from x equals -2 to x equals 10. With the ribbon, we can also draw snakes as shown. We can calculate the area between the snakes and the floor using a simple integration technique. Since the ribbon moves like a sine curve, we can estimate that the equation of the ribbon is 24 sine of 10x plus 50. Using this equation, we integrate it using a left Riemann sum. By splitting the horizontal length of the snakes into 60 increments, we sum up the areas of the 60 rectangles to find the area between the floor and the ribbon. We manipulated the ribbon to make a polar curve, a limacon, with an equation of 23 plus 48 cosine theta. Using this graph and polar calculus, we are able to find the area inside the outer curve but outside the inner curve. Bodies can also make different shapes, like a donut. As you can see, the concavity of the body changes as Lily performs the jump. For example, the distance from her hip to her head looks like it is concave down and increasing. Therefore, we know that f prime is positive because the slopes tangent to her chest are increasing. We know that f double prime is negative because her chest is in a concave down shape, like the left side of a cup.